Now we're going to apply the Pythagorean theorem as a way of measuring distance between 2 points in a plane. And there are other ways to measure distances in 2 dimensions, and I'll talk about them when we talk about circles. I'll give you an example, one called the taxicab metric. But this way of measuring distance is what mathematicians thought of for many centuries, up until the early 1800s. That when math people thought about these things, they regarded themselves as living in a Euclidean world. Now, Euclidean means that the geometry is based upon right angles. So on a flat plane, your geometry is based upon horizontal and vertical. In three-dimensional space, there's also another perpendicular axis coming towards you. All right, so those are called Euclidean spaces or Euclidean planes, and the Pythagorean theorem is a Euclidean metric. It's a way of measuring distance in that kind of geometry. In the early 1800s, mathematicians got to thinking about this and realized that well, we don't live in that kind of world, especially because we live on the surface of the Earth, which is spherical. And triangles have more than 180 degrees on a sphere. Parallel lines can meet together at the poles. And so they got to think about these other ways of looking at things, and began investigating other kinds of geometry called non-Euclidean geometry. And ultimately, the physicists found this to be very, very useful and important. In fact, it was Einstein who theorized that space could be distorted by various forces like gravitational force. And in fact, that was actually observed to be true through experimentation. All right, well, let's, for now, I'll stick to the Pythagorean theorem. But I want to show you another way of measuring distance called the taxicab metric when we talk about circles. And so we'll come to that later. All right, so let's suppose I have 2 points in the plane. And one point is here. One point is, let's say, down over here. And I'm just making up numbers. Let's suppose this is at the point negative 11, comma 6. And this one is 17, comma negative 4. All right, just made those up. Now, I want to know what is the distance between these 2 points. Okay, so I'm going to call this D. And it ends up being the hypotenuse of a right triangle, which is normally called C, but I'm going to call it D for distance. Well, what's wonderful about our XY plane is that we can easily measure distance in 1 dimension. And so if I look at it this way, if I drop down vertically and then move over horizontally to get from this point to that point, then I've created a right triangle. And let's see, the side of this triangle has length what? 6 and negative 4. It's 6 units here and 4 units there. It's 10 units. Now we could get that through subtraction. 6 minus negative 4 is positive 10. All right. And then what's the horizontal length, or the base of the triangle? I jump from minus 11 to positive 17. That's a distance of 28, isn't it? So 10, 28. And then there we go. We can find our distance. So if I do so, the Pythagorean theorem tells us that 10 squared plus 28 squared equals to D squared. And now it's a simple matter of solving that little equation. Let's say this would be 100 plus 784, I think, equals D squared. So D squared is 884. So D would be what? It would be the square root of 884. A little technical note, when you solve this quadratic equation, you're supposed to have a plus or minus there. Well, we don't measure negative distances, so here I can get by ignoring the negative because there is no such thing in terms of measuring distance. So the distance is the square root of 884. I'll write that out. The distance is the square root of 884. And I want to approximate that. Unfortunately, I left my calculator in the other room, so I'm going to pause for a moment while I get the calculator. There, that was fast, wasn't it? All right, square root of 884 is around 29.73. So around 29.73. It would be units. You know, if I was in feet, it would be feet, for example. So, is that a reasonable answer? Oh, I think so. It's got to be more than 28, but not too much more. So that looks right to me. So there's an application of Pythagorean theorem, and let's do one more.